Okay, so good evening, everyone. So today we are in the week three problem solving session of the NPTEL course NMR Spectroscopy for Structural Biology. So I hope all of you have gone through the week three lectures. Okay, so in the last live session, we were talking about the spin-spin splitting and the n plus one rule to understand the splitting of the peaks. So we learned about the Pascal's triangle. So if peak can split into a doublet, a triplet, or it can be doublet of a doublet. So, so a little bit part of that spin splitting is left. So we will start with that part, and then we will learn in more detail about the FT-NMR, practical aspects of NMR, FT-NMR, which were covered in great detail in week two, and also some part were covered in week three as well. So we will go through those concepts. Because I'll wait for 2 more minutes so that other learners can join, and then we will start with today's session. So in today's session, we will quickly revise the concepts of FT-NMR, Fourier transform NMR. We will solve a few questions related to those concepts, and uh, and we will quickly revise some of the concepts which are covered in week three. That will help you in solving the assignment questions. I'll start sharing the slides for today. I hope the screen is visible. Okay, So good evening, everyone. I am Akash Jyoti Pathak. I am a PMRFTA for this NPTEL course on NMR spectroscopy for structural biology. So this course is is a rerun course which has been taken by Professor Ashutosh Kumar and Professor Ramakrishna Hosur sir. Uh, so starting with some of the few questions related to the spin splitting were left. So we will go through the concept of spin splitting, and then we will move to the FTNMR and the solvent suppression part. Okay. Uh, so so we were already discussing this part, right? Uh, so, uh, so what is the origin of the spin splitting? So what happens is the spin splitting arises because hydrogens on adjacent carbon atoms can sense one another. So for example, if you can see this figure, so in this figure you can see that there are two carbon atoms, Ca and Cb. Now this carbon A atom has two groups. It is attached to two R groups. Similarly, carbon B is attached to two R groups, and now this carbon A is also attached to a proton, which is labeled as HA, and carbon B is also attached to a proton, which is labeled as HB. So what happens is the hydrogen on carbon A. So this is in very layman term, without going into very into the quantum aspects or in very detail. So what we can understand in a physical sense is that the hydrogen on carbon A can sense the spin direction of the hydrogen on carbon B. So in some molecules of the solution, the hydrogen on carbon B has spin plus half, which is called the X-type molecules. In other molecules of the solution, the hydrogen on carbon B has spin minus half. So, for example, if there are 100 molecules this particular uh, this particular compound, this RCACBRR. So if we consider that there are 100 such molecules of this compound, then there can be like 50 molecules wherein this proton, HB proton, can be in the plus half state, and there can be other 50 molecules wherein this HB proton can be in the minus half state. So this proton A absorbs. So what happens because of this particular in some of these molecules this is exist in one spin existing as one spin type, and in some other molecules it is existing as another spin type. So accordingly they will have different energies associated with them. So the magnetic field, because they're spinning, the magnetic field around them will also be different for both these cases. So this proton A absorbs at a slightly different chemical shift value in type X molecules than in type Y molecules. So since in a given solution there are approximately equal number of X and Y type molecules, so X type molecules are those in which the HB molecule was in the plus half state, and Y type molecules are those in which the HB proton was in the minus half state. So because there are approximately equal numbers of this X type and Y type molecules at any given time, the two absorptions of nearly equal intensity are observed for proton A. So the resonance of proton A is said to have been split by proton B, and the general phenomena is called spin splitting. So what happens is that this HA proton, as I discussed, that this HB can sense the environment around it. So this HB proton will result in splitting of this HA proton. So as a result, you will get. So this is there is only one proton. So if we follow the n plus one rule, so this HA, the frequency of this HA proton will be split into two. So 1 plus 1, you will get a doublet. Similarly, this HB proton will be split by this HA proton into doublet. So that is why you are getting two doublets over here. So one is for the HA proton and another is for the HB proton. And they are of the same intensity because why are they of the same intensity? So in case of a doublet, both these are the two peaks that we get, they are having an intensity of 1:1, because there are almost equal numbers of the X type molecule and the Y type molecule. Okay, but So if we see this example again, so here also what will happen? So this if we see this molecule, so the first molecule will would only give a single NMR peak, since proton A and proton B have the same chemical shape value and are identical. So here what is happening, if we see the chemical environment of this proton, HA proton, then this chemical environment of this HA proton is that it is surrounded by this two electronegative atoms, right? Bromine and chlorine. Similarly, this HB proton is also surrounded by the same electronegative atoms, bromine and chlorine. So as a result, there will only be a single NMR peak. Okay, so because the chemical environment for both these protons are the same, so that is why you will get the chemical shift for both these protons will be the same, because they are having the same chemical environment. So you will get a single NMR peak. Okay. But if you see these two protons, for this molecule, so this is your first molecule and this is your second molecule. So if you look at the proton of this molecule, this proton, HA proton, is surrounded by is near to two electronegative atoms like chlorine and chlorine. So these two electronegative atoms are different, but different from the groups which are present near the HB proton.
Hello, sir. Excuse me,
Yeah,
sir.
yeah, please.
Sir, can you tell me the loud is? It's very speed you are talking that we can't
Okay,
understand that.
okay. So which part do you want me to repeat?
No. Continue, sir. Continue from here only, but you are going with speeds.
Okay. Yeah.
Okay, thank you.
Okay, so if we so for this molecule, so first consider this molecule. So if we consider this molecule, bromine, carbon. So if we plot the proton NMR spectra of this molecule, okay. So how does the proton NMR spectra look like? So the proton NMR spectra will have what? It will have delta ppm on the x-axis, right? And you will have absorption frequencies on the y-axis, right? So your absorption, your y-axis, what does your y-axis give? Gives your absorption frequencies. Okay, or basically it provides you the intensity of the peak. Okay, intensity of the peak. So for this molecule, if you want to plot the proton NMR spectra for this molecule, then for this molecule you will only have a single proton peak. Okay, you will have only a single proton peak. Why is it so? Because if you look at the chemical environment of this HA proton, so this is your HA proton. So this HA proton, its chemical environment, so it is surrounded by two electronegative atoms like bromine and chlorine, and then it is having this particular big group. Okay. Now if you look at this particular proton, it is also surrounded by the same groups, bromine, chlorine, and this bigger group. Okay, so the chemical environment of HA proton and HB proton, they are the same, right? So as a result, what will happen when you will apply that particular RF pulse, both will show the both will be shifted by the same frequency. So you will get only a single peak for this molecule. Now if you want to plot the NMR spectra for, so I hope this point is clear, right? Because the chemical environment for this HA proton and HB proton, they are the same. That is why you only get a single peak for this particular molecule. But if you plot the proton spectra for this molecule, so here also you have two protons, right? HA and HB. But the chemical environment of HA is different from that of HB. So HA is nearer to the two chlorine atoms. But if you see the chemical environment of HB, you can see that it is surrounded by acetate ions, OCH3, OCH3. Okay, so that is why what will happen, there will be you will have two different peaks. First of all, you will have two different peaks, and because the chemical environment, this particular proton will result in a doublet of this particular proton. So you will have, Okay, so now which is more electronegative, chlorine or acetate? We had discussed it in the last class, right? So if we look at the electronegativity of chlorine, then it is more compared to OCH3. So it will be more downfield shifted compared to the acetate ion. So your AHA proton will be more downfield shifted, which means that it will have a higher ppm value. Okay, and this will be B. Now, because this proton, so this proton will cause a n+1 splitting of the HA proton, and similarly, this HA proton will cause a splitting of this HB proton. So you will again get a doublet of the proton B. This is your delta ppm. So it goes in this direction, right? So from this is 0 ppm, and as you go from right to left, your ppm increases in case of a NMR spectra, right? So so the first point, so for this molecule, what you are getting, what you will get is that you will first of all get two different peaks for the two different protons, and also the peaks will also be split into doublets. Okay, since proton A and B are not identical, and there will be a two doublet spectrum that will be observed. Now, we had also, this part was also covered in the lecture, the coupling constant. So the strength of coupling is called coupling constant and is denoted by the symbol Nj for two spins separated by N bonds. So, here in this case, we were seeing that this what are the how many bonds? So how many bonds are there between the two protons? That is basically giving you the coupling constant. So one bond coupling constant are for the so for the heteronuclear cases C13 1 each, N15 1 each, P13 1 each. So this been paired. So for each of these different pair, you have a different J coupling constant. So for proton, the J coupling constant is lies in the range of 5 to 20. For carbon 13 and proton, it is around 100 to 250 hertz. For 59 and proton, it is 80 to 100 hertz. For P31 and proton, it is a few hundred hertz. So, so basically, what this shown in this figure is that your this if there are two state alpha A beta X, so there can be two populations, right? Your A nuclei can exist in the alpha state, or it can exist in the beta state. Similarly, your X nuclei can also exist in the beta state, or it can exist in the alpha state. So now if you apply this particular frequency which is specific to the nuclei A, then it will this A nuclei is getting will transition to the B state, to the beta state, right? So this alpha A state, it will the nuclei will transition to the beta A state. So this is given as nu A. Now if you excite this particular X nuclei, if you apply that particular frequency nu X, then this alpha, the nuclei which was present in the X nuclei which were present in the alpha state, they now transition to the beta state. So that is nu X. Similarly, your beta A can again go to, so if you apply this nu A2, it will go to alpha X. So there can be there can be, so as we were discussing, right, that n+1 rule. If you excite that particular nuclei, you are getting two peaks. So these are the two peaks that you were observing, that you would observe: beta A beta X, alpha A alpha X. So this is resulting in a doublet. Okay. So, what is the concept of the strong coupling and weak coupling? So, the spins are labeled as A, B, C, etc. So, the choice of the labels depends on the difference in the resonance frequencies relative to the coupling constant. So, there can be different system. So, these things have you can there is you can skip. So, in detail, this understanding is not required, but because we are mainly in this course we are mainly restricting ourselves to this structural biology part. But for now, so for just for knowledge, you can understand that there are three, like there can be different systems. So the AX system is, so if the spin A and X have widely separated resonance frequencies compared to their J coupling constant, so that is a AX system. AB, there can be an ABX system. So spin X is widely separated from both A and B. Spin A and B have similar resonance frequencies relative to JAB. There can be AB, ABC are strongly coupled system. These AX, AMX, AMQX, these are weakly coupled systems. So weakly coupled systems are these AX, AMX, AMQX systems. The relative magnitude of the coupling constant and the chemical shift separation determine whether the spin system is weakly coupled. So basically your J value will determine whether the two nuclei are strongly coupled or whether they are weakly coupled. So larger the J by delta ratio. So when we are talking about the strength of coupling, we have to consider this ratio, J by delta ratio. So this J by delta ratio, if it is larger, then we say that the two nuclei are strongly coupled. If the ratio is smaller, then we say that the nuclei is weakly coupled. So the heteronuclear nuclear spin system always belong to the weak coupling category, and strong coupling situation occurs in homonuclear spectra. Okay, so here also you can see that for your, so you can see the coupling constant values in this table as well. So you can see that for homonuclear system, your coupling constant values are in the range of 5 to 20. So this is the ranges. If this value is this J range, this J Hertz range is 5 to 20, means it is very strongly coupled. But heteronuclear coupling, if you see that proton and carbon 13 or proton and 15 and nitrogen coupling, their values are larger, means they are very weakly coupled compared to homonuclear. So remember this point that the homonuclear coupling are stronger compared to the heteronuclear coupling. Okay. So so here what has been shown is that like 3 to 1 transition, 4 to 2 transition, 2 to 1 transition. So this the when the J by delta is infinite, the two outer transitions have zero intensity. So you can see that this as you are as so this is a singlet. So this is a singlet. Then this is a doublet. So as your splitting is taking place, you can see the outer periphery, the periphery peaks that you are getting. They are almost having zero intensities. Okay, then this is J by delta 0.5. So as your this J by delta value, as they are as they are decreasing, your coupling is decreasing. So that is why if a nuclear, so your J by delta value basically gives you a measure of how strongly or how weakly the two nuclei are coupled. So you can see over in this figure also, you can see the same concept that as your J by delta value is decreasing, your coupling, your nuclei are becoming weakly coupled. So the greater the J by delta value, the more strongly the nuclei are coupled. Okay, so that is only so in this figure that thing is only shown here. So for J by delta 0.1, this is like the least value of J by delta in all these cases. So that is why they are very weakly coupled. Okay. So when the J by delta is infinite, so the spins, it means that the spins are equivalent. The outer two transitions have zero intensity, which means that the sine 2 theta is equal to 1, and the inner two transitions have the same energy. So this is the case. So the first case, so if your J by delta is infinite, then you will get a singlet basically. So the two, you will have a single peak. Both the protons are both the spins are equivalent. So that is why your you will have that your nu one and nu two becomes equal, and you get a single frequency value, that is nu. So it is half nu one plus. So this frequency, what will be the value of this frequency? It will be half nu1 plus nu2. So the parameter theta appears in strong coupling and changes the intensity and frequencies of the transition. Therefore, it is called the strong coupling parameter. Okay. So these calculations and everything, they for this understanding, we have to like derive all those Bloch equations and things which were discussed in the lecture. But we will but for revision we can see that as the j, basically the j by, what you have to understand is that j by delta value gives you the measure of coupling. If it is strongly coupled, then you will have higher j by delta value. If it is weakly coupled, it will have lower j by delta value. And your intensity is actually, you can get the intensity of these peaks by this equation 1 minus sine 2 theta, where sine 2 theta is j by 2c, and this 2c can again be written as root over delta square by j square. And if you divide it by j, then 1 plus j by delta whole square. So this is your sine 2 theta. So your theta parameter appears in strong coupling and changes the intensity. So you can obtain the intensity of the frequencies from this sine 2 theta value. Okay. So now from the concept that we understood, tried solving this question. So if the coupling parameter theta is equal to 22.5, what type of coupling does the spin system experience? Is it strong coupling, relatively strong coupling, weak coupling, or relatively weak coupling? So if your theta is equal to 22.5, so you can actually put this value in this equation. Sine 2 theta is equal to j by j square plus delta square. So for theta equal to 22.5, your 2 into 22.5 will be sine 45 degree, right? Sine 45 degree. And so now you can write that sine 45 degree equal to 1 by 1 plus j square by delta square. So if you like put this the put the values in this equation, then what will you get? You will get j by delta value is equal to 1. So because your j by delta value becomes equal to 1, and j is nearly equal to the chemical shift, coupling constant is nearly equal to chemical shift. So this is the case of relatively strong coupling. Okay. So you have to use this equation. So basically you have to put the theta value 22.5 in this equation. So when you put the value of 22.5 and you calculate the j by delta value or delta by j value, if you like divide it by j on both sides, then you will have this equation. Finally, this will be the form of equation that you will get. So this one, if you calculate, so this is sine 45. Sine 45 is 1 by root 2, right? So 1 by root 2, and if you square both sides, then you will have half, right? Half, and then you will get 1 by delta by j whole square. So 1 by, so if you solve this equation, like 2, right? So delta by j whole square will be equal to 1. So you will get delta by j will be equal to 1, right? So your delta value becomes equal to j. So that it is a case of very strong coupling. Okay, this case. So if your j by delta is equal to 1 is a case of strong coupling. So we had discussed this question already in the last lecture. Just give me a second. I think I have. So now answer this question. So the proton. So I hope till this point, this part everything is clear. Are there any doubts? So try to answer this question. So the proton spectrum of a vinyl chloride will consist of. So this was one of the questions which were asked in your assignment. So option A is a doublet and a triplet, two doublets, two triplets, three doublet of doublet. So like if you draw the structure of this molecule. So here you can see that there are three protons, right? A, B, and C. So since there are three protons, now what will happen is this proton is different is in a different chemical environment. This proton is in a different chemical environment. This proton is in a different chemical environment. So this proton. So when you want to understand the peak splitting of this proton A, HA proton. So this proton A will be split by this proton C, right? And it will also be split by this proton B. So this proton C will split the proton A into doublet, and proton B will also split the proton A into doublet. Similarly, for proton B, the if you look at proton B, the same case will happen. So your proton B will be split by proton A. So you will get a doublet, and then proton B will also be split by proton C. So this will again give you a doublet. Similarly for proton C, so these are all these three protons are basically non-equivalent. Okay, so because these three protons are non-equivalent, and you had learned that n plus one rule. So this n plus one in this n plus one rule, this n is actually the number of equivalent protons. But in this case, you are seeing that all the three protons are non-equivalent. So this proton A will be split by this proton C into a doublet, and which is this is a non-equivalent proton. This is also a non-equivalent proton, and it will also be split by proton B. Similarly, for this proton C, it will be split by proton A into a doublet, and it will be split by proton B into doublet. So you will have three doublet of doublets. Okay, so you will have three doublet of doublets. Okay, so if we see this proton A, so this proton A will be if it is split by proton C, so the coupling constant will be what? It will be JAC. So it will be split into two, and then again this particular peak split, the molecular transition that we see, that will again
Excuse me,
be,
sir.
yeah.
The screen is not visible. That
Screen is not visible.
okay. Okay. Now it's okay, sir. Now it's okay.
No, it's okay. Is it okay now?
Okay, sir. Okay.
So So the this proton A is being split by this proton C into a doublet, and again this split, the nuclei that you the splitting that you get, that is again being split by proton B. So you again get JAB. So in the end you have like three. You have like four different. So it will look like this. Like 1:3 is to 3 is to 1. Right. This will have, if we look at the intensity, then the middle two peaks will be having a higher intensity than the peripheral peaks. So 1:3 is to 3 is to 1. So that is, we will get doublet of doublet. So this is an example of complex coupling. In this case, a proton is coupled to two or more sets of non-equivalent protons. So proton A is coupled to proton C, and it is also coupled to proton B. And so both of these are non-equivalent protons. So proton A is coupled to both proton B and proton C, but with two different coupling constant. Right? Why will they have two different coupling constants? So because they are having different chemical environments. Okay. So HC. HC is in trans to HA, or HB. So if we like represent it in a different way, then we can say that HC is in trans to HA across the double bond and splits the proton A signal into a doublet. The HA doublet subpeak is split again by HB into two more doublets. So that is the case of geminal coupling. So this pattern is referred to as doublet of doublets. In a similar manner, the HB and HC proton are also split as doublet of doublets, resulting in three doublet of doublets in the proton NMR spectra. So your proton A will be split into doublet of doublets, proton C will be split into doublet of doublets, proton B will also be split into doublet of doublets. So you will have three doublets of doublets, three doublet of doublets. So the answer is option 4. Okay, so now let's understand the Fourier transform NMR, which were covered in week 2, and a part of it was also covered in week 3. So what have we learned about the Fourier transform NMR is that compared to the continuous wave NMR, what happens in a continuous wave NMR is we vary the magnetic field. So when we vary the magnetic field in a s- the at a particular, the magnetic field is associated with a particular frequency, right? U equal to gamma b naught by 2 pi. We learned this. So when we are varying the magnetic field in case of a continuous wave NMR, so we had learned this in the last lecture as well. So when we are varying the magnetic field, the frequency is also varying. So at a particular frequency, what will happen? This frequency will match the Larmor frequency of the nuclei. And so when this frequency will match the Larmor frequency of the nuclei, there will be we will get an absorbance peak. Okay, but in case of Fourier transform NMR, what we are doing, we are applying short pulses of radio frequency. So this, why are they called uh, RF pulse? So these are called as RF pulse because they are called as RF pulse base because we are applying radio frequency energy for very short duration. So its duration is like around 10 microsecond. So these short RF pulses are RF frequencies or radio frequencies are applied for very short duration. That is why they are called as RF pulse. So we apply RF pulse. So an RF field applied for a short duration tau is called RF pulse. So you can see in this figure. So this figure was there in the lecture slide. So you can see that at particular. So we are for a very short time tau, we are applying a particular frequency, radio frequency, and this radio frequency which is applied for a very short time tau is called as RF pulse. Okay, so due to Fourier relationship between the time and frequency domains, a short RF pulse excites a broad range of frequencies. So what will happen is that when we apply that particular RF pulse, all the nuclei, so the nuclei which are having the frequency that which is equivalent to the frequency of the RF pulse, all those nuclei will be excited simultaneously. So that is what is written. So this short RF pulse will excite a broad range of frequencies. So you can see here. So this is in the time domain. So when we are applying this RF frequencies, we are applying it for short duration tau. Now this is in the time domain, and the this everything that we get is in the time domain. So we need to do a Fourier transform to convert this time domain into frequency domain because the signal that we observed in the NMR spectra, they are all in the they are we get the frequency peaks, right? So the Fourier transform of this time domain converts this time domain into the frequency domain. So only the relatively flat portion of the excitation profile is used approximately, and this is approximately equal excitation efficiency across the NMR spectral region. So when this is converted into the frequency domain, we can see here that a broad range of frequencies are excited. So you can see that here we get the frequency peak that we get, that is quite broad, but we consider the middle value, this one, that the middle this frequency will be considered as the frequency of that particular nuclei. Okay. So basically if you are applying 10 microsecond, and if you want to convert it into frequency, then this 10 microsecond will be converted into this 1 by 10 into 10 to the power minus 6. So it will be 1 by 10 to the power minus 5. So at one end you will, so this will be 10 to the power 5, right? So if you are applying a tau, this RF pulse is applied for 10 microsecond, then 10 microsecond like, will correspond to 10 to the power 5 hertz, right? So frequency, if you want to convert the time domain into frequency domain, you have to basically divide it by 1. So if you divide it by 1, you will get the frequency. So this is 10 to the power 5 hertz. So here, so 1 by tau frequency at one end, and another end it will have 1 by tau frequency. That is, so this will correspond to 10 to the power 5 hertz. Okay, so what happens is basically, so we had discussed the concept of bulk magnetization, equilibrium magnetization in detail in week one itself. So, so what is happening is when we are providing this short duration of RF pulse, so the magnetization, this longitudinal magnetization. So in the equilibrium state, your bulk magnetization will be oriented towards the z axis, right? So when you are applying this RF pulse, this z magnetization will move to the x axis. So for example, we are considering that when we are applying a 90-degree pulse in the z direction, this pulse is now, this transverse magnetization has come to the x axis. So now what will happen? So for a short duration tau of of RF pulse, the magnetization tilts away from the z-axis by an angle theta in the xz plane. So this theta, so the angle by which this bulk magnetization is flipped can be given by this equation theta equal to omega r tau, or theta equal to minus gamma h1 tau. So this is also called as the flip angle. Flip angle is basically when we are applying a particular radio frequency pulse, the angle by which the Z magnetization or the longitudinal magnetization flips from the Z axis to the XY to the XZ plane. Okay, so that is the flip angle, and it is given by this equation, that is minus gamma h1 tau. So basically, so here you can see that this flip angle is controlled by the duration for which the RF pulse is applied. So this so the duration of the RF pulse is plays an important role in what the flip angle will be. So this concept was, so that this concept gives us another leads to another concept which is called as the free induction decay. So what happens is when a 90-degree pulse will rotate the magnetization from the z-axis into the transverse plane. So your transverse plane is xy plane, and your magnetization, so all the nuclei are precessing about the z-axis, right? So if this is your z-axis, so all the nuclei which is present in your sample, they're precessing about the z-axis. And if we break this break the all the nuclei into two components, the z component and the xy component, then what happens is that if we add up all the components in the z axis, then we get a net magnetization in the z axis, which is called as a bulk magnetization. So when you are applying an RF pulse in the z axis, this bulk magnetization which is oriented in the z axis, that will move to the transverse plane, which is called the xy plane. Now once this RF pulse is removed, the rotating frame RF field is no longer present, and the magnetization begins to evolve under the influence of static magnetic field. So the magnetization now precesses in the transverse plane while simultaneously returning towards equilibrium. So what happens is that in the equilibrium state, all your we had learned that all the magnetization which is in the xy plane, they all cancel out each other, and we have the net magnetization along the z direction. And this net magnetization which is in the z direction is called the bulk magnetization. Now when we are applying an RF pulse, what will happen, this z magnetization moves from the longitudinal plane to the transverse plane. Now as a result, what happens is that the xy components which were adding up to give a net value of 0, that now no longer remain 0. So now this transverse components that were there, now they start to precess about the transverse axis. So if this is your xy plane, this is your z axis, and this is your xy plane. This is your if you consider this as x, this as y. So your magnetization will precess about this xy plane now. Once the RF pulse is removed, once the RF pulse is removed, the nuclei will start precessing about the xy plane. Okay. So that is what is written here. So the transverse magnetization. This transverse magnetization produces a detectable signal in the receiver coil. So if you place a detector in this XY plane, then this decay in this transverse magnetization. So this is your transverse magnetization. So once the RF pulse is removed, there will be a decay in the transverse magnetization, and there will be a growth in the longitudinal magnetization. So that decay in transverse magnetization is recorded as FID basically. So this precessing magnetization induces a voltage in the detector. Different nuclear spins precesses at different frequencies. Therefore, each frequency component contributes to its own signal, and the observed signal that is obtained is the superposition of all these frequency components. So after the RF pulse, the transverse, so basically what happens, so once this RF pulse is removed, there will be a decay in the transverse magnetization, and we can place a detector and record this relaxation in the transverse axis XY direction, and that is recorded as an FID basically. So this decay in frequency that you are getting, that is actually a superposition of all the decay of all the nuclei that is present. So there are different nuclei in the sample. Like there can be proton nuclei, carbon nuclei. So all these and all these protons are in different chemical environment as well. So all these nuclei will have a different frequency. So this particular signal that you're getting, you can again decompose, you can Fourier transform, and you can decompose it into individual signals, right? So when you do a Fourier transform, you can break this particular, so this signal that you're getting, that is a combination of different frequency signals, and different sine and cosine waves. So you can break it up into different sine and cosine waves, and when you add all these sine and cosine waves, then the resultant frequency that you get, that is basically this free induction decay signal that that is recorded by the instrument. Okay, so after the RF pulse, the transverse magnetization will begin to decay. The decay occurs because of the transverse of spin relaxation, or the T2. This is on the T2 relaxation. So this excitation is called the signal free induction decay. So after this RF pulse is removed, the time domain signal that we get. So this is your time, right? Time domain signal that we get, that is called the free induction decay. So basically, your FID is a combination. It is a superposition of all the frequency superposition of all the frequency of the nuclei which is present in the sample. So when you deconvolute it, when you do a Fourier transform of this time domain into the frequency domain, then you can get the frequency information of all the nuclei which is present in the sample. So your FID contain the frequency information. The oscillation frequency will correspond to the resonance frequency, and different nuclei or resonances contribute to different oscillation frequencies. So basically what will happen, this reinduction decay that you get, that is superposition of different nuclei. So for example, a particular nuclei can have this signal. A particular There can be another nuclei which is showing this type of decay, like it is showing a decay like this. There can be a nuclei which is showing a decay in this form. Okay, there can be a nuclei which is showing something like starting here. There can be different amplitudes as well, right? So it's some can have shorter amplitude, some can have longer amplitude. The frequency, the wavelengths can be different. So superposition of all these different decay from all these different nuclei will give you the free induction decay signal. And then this is Fourier transform. So this is in the time domain. When you do a Fourier transform of this, and then you get the signals. All the different signals can be deconvoluted, and you can identify that this is for this particular nuclei. This can be, this signal is from another nuclei. This can be from another nuclei. So you can, so when you do a Fourier transform and convert it into the frequency domain, only then you can get the information of all the frequencies which were present in the free induction decay signal. Okay, so it also contains the relaxation information. So the decay of the signal with the, so your basically your methyl region, your amide region of your protein, so all these different regions, your lysine, epsilon amide lysine regions will have different relaxation if we talk about protein. So there will be different regions will show different relaxation also. So from that information you can actually understand that which region of a protein is more flexible, which region is more rigid. So this T2 value, so we will learn about this in the later lectures, but this free induction decay provides a lot of information about the frequencies and the relaxation information about the different regions present in the sample. So FID is a time domain signal. The NMR spectra are normally displayed in the frequency domain, right? So the Fourier transformation converts the time domain FID into the frequency domain spectrum. Okay, so free induction decay is your time domain signal. It is a time domain signal. When you do a Fourier transform, you get the frequency domain signal. Okay, this is a frequency domain signal. So the individual frequencies present in the FIT appear as individual resonances in the spectrum. Although the RF pulse initially excites a broad range of frequencies, the detection process records the frequency components corresponding to the actual NMR frequencies. So when you, that is what I was explaining, that when you do a Fourier transform, only then you will be able to deconvolute all the frequencies and all the NMR resonances which were present. Okay. So here also you can see, so this was explained very uh, explained in very detail in this lecture, that you initially you are having all the, so you are having different, so in this case you have been given an example of two nuclei. One is K nuclei and another is the L nuclei. So you can see that during equilibrium, these both these two nuclei have their bulk magnetization, or the net magnetization is oriented in the Z direction. Now when you are applying a 90-degree X pulse, so this 90-degree X pulse will flip the magnetization from the Z axis to the Y axis. Okay, so now what is happening, your bulk magnetization has flipped from the Z direction, so both the nuclei have now come to the Y axis. So that is why, so initially you were having this Iz equal to IKZ plus ILZ. Now when this 90-degree X pulse is applied, you are now getting signal in the Y direction. Okay, so that is why it has become IY. So IY is containing signal from both IKY plus ILY. Now when this RF, now you are now you have removed the RF pulse. So now the RF pulse is removed, so for the duration T. Now in this duration T, in this duration T, what will happen, this nuclei will start to the transverse magnetization. This transverse magnetization of this particular nuclei will decay, and for the L nuclei also it will decay. So now the decay will now this decay in the signal is what is recorded by an FID basically. So this has a particular this nuclei, K nuclei will have a different decay than the L nuclei. So that is why the signal that you observe is actually IKY cos omega KT, and your L nuclei will have another it's a frequency of decay will be different, so it will be ILY cos omega LT. So function and this green color function, that will be a superposition of all the of the decay of these two nuclei. Okay, so that is what is explained here. So many frequencies are excited simultaneously, and all of these nuclei will produce an FID. So the complete spectrum obtained will be obtained after Fourier transformation. So multiple FIDs can be accumulated before Fourier transformation. And also one more thing that was discussed is that Fourier transformation is a linear operation, because multiple FIDs can be added and Fourier transform one. So you can basically add up all these signals. So you Fourier transform of GT plus Fourier transformation of G1T and G2T. So all these So when you are doing a Fourier transform, now you can deconvolute it into different frequency signals. So your this is your free induction decay. When you do a Fourier transformation, you can deconvolute it, and you can now observe the separate resonance frequencies of the different nuclei. So what were the advantages of FTNMR over continuous wave NMR is that FTNMR gives you more signal to noise ratio improves for FTNMR compared to continuous wave NMR, and we can also detect rare nuclei such as 13 carbon and 15 nitrogen. So rare nuclei means that abundance of these nuclei are less. So for a detection of detection of signals from these nuclei, FTNMR gives can give you better signals compared to this continuous wave NMR. And we can also analyze low concentration samples. So we had discussed all these in the last lecture as well. So we can do several scans. So as we increase the number of scans, then the signal to noise ratio can be improved, is proportional to number of scans. We have understood this concept also. And we can also study kinetic phenomena. We can study unstable or short-lived species. So now another thing that was discussed is that, so this is how an FT NMR so an NMR spectra which is working on the principle of FT NMR is looks like this. Okay, so for FT NMR, what is required? We require a high magnetic field. Okay, so how can we produce high magnetic field? So high magnetic fields can be produced by superconducting magnets. So these are the superconducting magnets are required. So now for superconducting magnets, maintaining the superconducting magnets, the important thing is that you have to keep them at very low temperature. So such low temperature is provided by the helium. Okay, so it is provided by the helium. And this one another important thing about the super conducting magnets is that they can produce very stable magnetic fields. They can produce very large magnetic fields, and they can produce very homogeneous magnetic field. So throughout your sample, the magnetic field should be homogeneous. So if you want a very uniform signal, so higher. So why do we require higher magnetic field strength in case of NMR? Why is it desirable? Is because with increase in magnetic field, we get higher sensitivity, and we also get greater dispersion of NMR signals. These concepts we had learned when we were discussing in week one itself. We have learned magnetic fields. So so for producing very strong magnetic field, what will be required? You will need to pass very large currents. So for passing very large currents, what will happen? So when you will pass very large currents, what will happen? A very large amount of heat will be generated as well. So to reduce the heat generated, you have to keep this superconducting magnets in low temperature. Okay, so that is why. So that is what is written here. So large currents will cause significant heat generation, and as a result you will require large cooling will be required, and also large physical space is required. So for this, what is done, superconducting magnets were developed to overcome the limitations of conventional electromagnets. Okay, so for so these superconducting magnets allow very stable magnetic fields. They will allow very large magnetic fields to be produced, and they will produce very homogeneous magnetic fields. So what are superconducting magnets? Is that a superconducting coil? So here also you can see that now since the temperature has to be maintained, so this was also explained in the lecture. So it's, because the temperature has to be maintained outside this helium, so liquid helium is present surrounding this superconducting magnets, and then periphery to the liquid helium there are again liquid nitrogen. A chamber is present, and in this chamber, liquid nitrogen is filled, so that the heat is not does not so that the temperature can be maintained inside these helium chambers. Okay, and the helium can be maintained in the liquid state, so it will not allow the heat that is generated to escape. And then outer to this liquid nitrogen chamber, there is a vacuum chamber. So these chambers are present so that the outer temperature or so that the temperature within the superconducting magnets can be maintained at a very low temperatures. So that is the main reason. So a superconducting coil has essentially zero electrical resistance. Because it has zero electrical resistance, now we can pass very high electric currents. So once current is established in the coil, it can continue circulating without significant decay. Therefore, a strong and stable magnetic field can be maintained for long periods. So when you the purpose or advantage of using superconducting magnets over electromagnet is that we can maintain homogeneous, strong magnetic fields for very long periods. And what is present in a superconducting NMR magnet? It contains a main superconducting coil. So you can see in this figure, it has a superconducting coil which generates strong magnetic field. It operates at very low temperature, 4.2 Kelvin. The temperature of liquid helium is 4.2 Kelvin, and the superconducting coil is immersed or cooled using liquid helium. Because you are passing very high current, the heat generated will be also very high, so you have to maintain it at very low temperature. So for this, what is used? Liquid helium. And surrounding the liquid helium, you have a liquid nitrogen chamber. So this provides an additional thermal insulation. So this is providing, just as I explained, that it is providing an additional thermal insulation. And then outer to the liquid nitrogen chamber, you have a vacuum chamber which provides further thermal insulation and minimizes heat transfer from the surroundings. So that is what I was explaining, that from the surrounding, the heat should not pass into the interior of the spectrometer, which is having the superconducting magnets. Okay. So that is why these insulations are present. So why liquid helium and vacuum is required? So that is what we explained, that the superconductivity requires extremely low temperature, and the superconducting coil therefore has to be maintained at cryogenic temperature like minus 197, minus 196, and liquid helium keeps the superconducting coil at approximately this 4.2 Kelvin. Okay, so liquid nitrogen provides additional insulation and a vacuum layer is present. Same thing is written over here. Okay. So now we are coming to the practical aspects of FTNMR. So there are a few questions that we will solve in this section. So the first concept that was covered in the lecture was carrier frequency and offset. So what happens is that in FTNMR, a short radio frequency pulse excites a range of frequencies simultaneously. Uh, so uh, so that is what we have been learning throughout for since a long time, that if we are applying that particular radio frequency pulse, it will excite all the nuclei simultaneously. Now the spectrometer has a nominal operating range of 500 megahertz. So if we consider that the spectrometer that we are using is having an operating frequency of 500 megahertz, so in that case, what will happen? So, but the practical case can be such that the actual spectral region of interest may not be centered exactly at this frequency. So we therefore shift the excitation region so that the region of interest is appropriately positioned. The amount by which the frequency is shifted is called offset, and offset is usually expressed in kilohertz or hertz. The shifted RF frequency used for a experiment is referred to as carrier frequency. Region the may not fall within the spectral range, so you have to shift. It can happen that you have to shift this particular frequency to a few kilohertz or a few hertz. So when you shift this particular NMR frequency to few kilohertz or hertz frequency to match the excitation frequency of the required nuclei, then that is called as the carrier frequency. Okay, that will be called as the carrier frequency. Now, what is RF? Another consideration in practical aspect of this Fourier transform NMR is that the pulse width. So we had discussed that the flip angle is equal to minus gamma h1 tau. So we can see that the duration of the pulse duration of the pulse is basically pulse width. Okay, so the duration of the pulse will control your theta angle, or will control your this flip angle. So that is why this the duration this duration has to be very so if you second, then it must be 10 microsecond. It cannot be like 10.1 or 10.2 microsecond. So it has to be very well calibrated. The instrument has to be very well calibrated so that the duration or the this pulse width is exactly equal to what is exactly equal to that 10 microsecond. Okay, so RF pulse is applied for a very short period tau. So this the duration for which this RF pulse is applied is called the RF pulse width, right? So a typical pulse may be around 10 microsecond. Short Such short pulses require very precise timing. Okay. The timing. So that is because why will it require? Why is it necessary that it is very precise? The timing is precise is because this timing will actually control the flip angle. So we can see that the flip angle depends on the magnetic field, pulse duration, and the gyromagnetic ratio. So if your pulse width is not accurately controlled, then there can be small errors in the pulse duration, and because of this small error in pulse duration, it will change the flip angle. And as a result, the if your flip angle is changing, then all the different aspects again, when we will talk about the spin echo and all these inepta based methods, so all these things will the signal that you will get, they will not be what you desired. Okay, so that is why the calibration of RF pulses is essential. Now the So now this detection axis, what is the detection axis? Whether you are detecting the FID, free induction decay in the x-axis or in the y-axis, that is also important, right? So you are in the steady state. In the steady state, your bulk magnetization is oriented in the longitudinal axis, which means that it is oriented in the z-axis. Now, when you are applying, or the net magnetization is oriented in the z-axis, when you are applying an RF pulse, so you are applying an RF pulse, a 90-degree RF pulse. For example, you are applying a 90-degree RF pulse. So first point is that it should be very perfectly controlled. This if it is 10 microsecond, then it has to be 10 microsecond. It cannot be 10.1 microsecond. And the third thing is that it has to be the what is your detection axis. That is also important, because if you are detecting the signal in the, so you are applying a 90-degree X pulse. So now your 90-degree X pulse will orient the Z magnetization into the Y direction. Now if you place your detector along the Y axis, if the detector is placed along the Y axis, then you will get the signal will be having this the free will follow this function m naught cos omega I t e to the power minus t by t to I. But if you are placing it along the x-axis, then it will follow a sine function. So if it is a sine function, then you will have signal that is starting at zero amplitude and then decaying. But if you are placing your detector along the y-axis, then your signal or your amplitude will start at the highest position and then it will decay. So basically what will happen is, when you are applying this 90-degree X pulse, your magnetization will shift to the XY plane. Now there will be some components in the X axis, some components in the Y axis. So whether you are placing your detector in the X axis or in the Y axis, that will determine what type of FID you will obtain. So if you place your detector in the X axis, you will get a cosine function. If you will get a sine function, if you place it in the Y axis, you will get a cosine function. So that is why your detection axis is also very important. So for example, you can see here that if the for example your detection axis is in the y-axis. Okay, so if it is in the y-axis, so remember this thing that if it is in the y-axis, you get a cosine function. You get a cosine function. If your detection axis detector is in the x-axis, if your detector is in the x-axis, you get a sine function. And when you Fourier transform a sine function, you get dispersive signal. When you Fourier transform a cosine function, you get an absorptive signal. Okay, so your detector, if it is placed in the x-axis, and there can be two cases, if your detector can be placed in the x-axis or it can be placed in the y-axis. So if you are placing your detector in the y-axis, then what signal it will capture? It will capture a signal m naught cos omega I t e to the power minus t by t2i. Okay, so y-axis captures your cosine captures a signal which follows a cosine function, and your x-axis, if your detector is on the x-axis, it will capture a signal which will follow the sine function. So when you do a Fourier transform of a sine function, you will get dispersive signal. So dispersive signal means it will have this type of spectra. And if you do a Fourier transform of cosine signals, then you will have absorptive signals. Absorptive signals means it will have this type of line shape. Okay, so that is what is shown here. So if it is a cosine function, you do a Fourier transform, you get absorptive signal. If it is a sine function, you do a Fourier transform, you get dispersive signal. Now it can also be, now your absorptive signal can be positive absorptive signal, it can be negative absorptive signal. So if your free induction decay is having this time domain signal is having this type of signal, then if you Fourier transform this free induction decay, you will get negative absorptive signal. If it is, if your sine function follows this negative if it is going from negative to positive, and if you do a Fourier transform of that, you give this negative dispersive signal. If it is moving from positive to negative, you get positive dispersive signal. So this is how a positive dispersive signal looks, and a negative dispersive signal will look like this. You have a negative signal and then a positive signal. And if you are so similarly, the same thing can be for the cosine function also. If it is starting from positive going to negative, then it will have a positive absorptive signal. If it is starting from uh, negative amplitude and moving to positive, then you will get a negative absorptive signal. So that is why the detection of your the detection axis is very important, whether you are placing it in the x-axis or the y-axis. If you are placing it in the x-axis, you will get a dispersive signal. If you are placing it in the y-axis, you will get an absorptive signal. Okay, now another thing that was discussed was the single detection versus quadrature detection. So what happens in single detection is that suppose we want to detect only the signals which are positive, only the signals which are positive, then in that case, so all frequencies relative to the carrier have the same sign. So all the frequencies that we want to detect are having plus sign, plus omega 1 plus omega 2 plus omega 3. Then in that case, there is no need to distinguish there. So since there are no negative signals, you do not need to you can only have single detection, right? You can, because you do not have to distinguish between the positive and negative frequencies, so a single detector is sufficient. But suppose there are your spectral region contains both positive frequencies and negative frequencies, then in that case you need a quadrature detection, because now you want the detector to detect both the positive frequencies and the negative frequencies. So you want to measure both in the transverse components simultaneously, the mx and the my component, right? That, so we learned that the mx component will have this sine function, will follow the sine function, and the my component will follow the cosine function. So if you want to detect both the cosine functions and the sine function, or the mx and my signals simultaneously, then you will require a quadrature detector. And if you have only positive signal, positive frequency signals, then a single detection is sufficient. So so always remember that your quadrature detector will have two detectors or channel. It will have two detectors, one for detecting the x signals, the components which are in the transverse plane. You have two you will get two signals, one is in the x direction and another is in the y direction. So you will require two detectors, one that will detect the x components and another that will detect the y components. So this is called quadrature detection. So the main difference about the single detection and quadrature detection is that in single detection you are having a single detector, so it will detect only the positive frequencies, and in quadrature detection you are having two frequencies. You are having two detectors, one that can detect the X magnetization components, and other that can detect the Y magnetization components. So you require two detectors. Okay. So now another thing is that signal digitization. So so your actual FID that you get, that your actual FID is a continuous signal, right? So your actual FID is a continuous signal, but the computer cannot store an infinitely continuous signal. So what is done is this FID is sampled at discrete time points. So at distinct, so at this particular point you will get a signal. This particular point. So at different points so when your computer cannot store such continuous signals. So at particular points, at particular time points, so this is your time axis, right? At particular time points you are capturing the, at discrete time points you are capturing the signal. So now this the signal that you capture, that is digitized. That is digitized means it is converted into binary form basically. Okay, it is converted into binary form and stored in the system. Now that can be for Fourier transformed, and we can get the frequency signal after Fourier transformation. So the time interval between consecutive point is called the dwell time, delta t. So your delta t is basically, so if you are capturing a signal at this particular time, and if you are capturing a signal at this particular time, then the difference between this two particular time point is called as delta t, or the dwell time. Okay, so the delta t is the time between two consecutive data points. The data point should be collected at uniform time intervals, and so what is dwell time? Dwell time is the interval between consecutive digitized FID points. I think this is clear. So your FID is basically a continuous signal. Computer, what it does is it the signal is sampled at discrete time points. So at this the signal the time between two or the duration between two discrete time points is called the dwell time. Now, another concept that was discussed in the lecture was the Nyquist theorem, or the Nyquist sampling. So, your FID will contain multiple frequencies, right? Because it is a superposition of multiple frequencies, all the nuclei, or superposition of the frequencies of all the nuclei. So, now, in the Nyquist theorem, what is followed is that the highest frequency that is present, if we consider that highest frequency as omega max, the sampling rate must be sufficient to represent this highest frequency. So if the sampling rate is such that it can capture that highest frequency, then all the other frequencies can be captured, isn't it? So at least two data points per cycle are required to be present. At least two data points per cycle are required to represent a frequency correctly. So your sampling frequency must be, at least it must be equal to the fmax, or it must be greater than the fmax. So fs is the sampling frequency and fmax is the highest frequency which is present. Okay. So the sampling frequency, or the frequency at which you are keeping you are capturing the signal, that should be at least be equal to the maximum frequency, or it has to be greater than that particular frequency. So your sampling frequency can be basically the dwell time. Yeah, if you divide it by the dwell time, that is your sampling frequency. Your dwell time is basically, so you have one point over here where you are capturing the signal, and you have another point over here you are capturing the signal. So this is your dwell time, this is delta t, and your, what is your sampling frequency? Your sampling frequency is 1 by delta t. Okay. So your sampling frequency, if it is 1 by delta t, then your delta t, again we saw that this delta t has to be, like if you do this one, delta t equal to 1 by fs, and your fs has to be 1 by 2 times f max. So your this dwell time, what should be the delta t that should be kept when you are recording the signal? That should be at least be less or equal to 1 by 2f max. Okay. So if the sampling is sufficient for the highest frequency, then it will automatically be sufficient for all lower frequencies. Now another thing that was discussed was the folding of signals. There are a few questions related to it. When we will solve the questions, you will understand it better. But what is the folding of signals? So what happens is you have kept a particular spectral width. Now, it can happen that the spectral width that you have selected is not covering the frequency you want to capture, or the frequency of the required signal is lying beyond the spectral width. So when you are capturing that FID, this signal, which is lying outside the spectral width, can fold within the spectral width, and you can get a signal at a very erroneous position. Okay, or at a very wrong. You can get a very wrong value of the frequency. So if you have to select your spectral width very carefully. So your spectral width should be such that it should cover all the frequencies. All the frequencies that you want to it should not be less than the frequency of the nuclei that you want to capture. Okay, so if it is lying below or less than the frequency of the nuclei, then there can be folding of signal, or this your signal, or the frequency of the signal that you want to capture can get folded, and you will get a folded signal. So that is what is shown here. So for removing this error, what you have to do, you can one way is to use a trial and error method. So you choose a large spectral width in the beginning, and then you can optimize it later. So if you choose a large spectral width, then what will happen, then this frequency which was lying outside the spectral width, now it can come within the spectral width, and you will not observe folding of signals, or you will not get a frequency at a different, or you are expecting it at say a 10 ppm or 8 ppm, but because you have not selected the spectral width, you are getting at a different ppm value, 4 ppm. So what you have to do, you have to keep the spectral width large, so that there is no folding of signal. So that is what is. Suppose if we choose a spectral width that is too small, thinking all our frequencies are inside this region, uh, then there may be, it can sometimes happen that we might think that yes, all the frequencies will be present within our spectral width, but there can be some frequencies which can, or there may be actually be a resonance outside the selected region. So if the sampling rate is insufficient, that resonance is misrepresented and appears at an incorrect position in the spectrum. So this is called folding or signal aliasing. If your sampling rate is insufficient, then this resonance will be misrepresented and it will appear at an incorrect position, which is called as signal folding. Okay, let's first do one thing. So now answer this question. So now we have understood some of the concepts of practical aspects of this FT-NMR. Try to answer this question. So in a quadrature detection, the carrier is placed at dash and requires dash detectors. So we discussed that for quadrature detection, I think the signal is network connection is lost. Is it? Okay, so we learned that what we have to do in quadrature detection is we are trying to capture both the transverse components, like, right? So we want to capture both the mx component and the my component. So for this we need to have two detectors. We need to have two detectors, one which will detect our cosine component, so your y component will give you the cosine function, and the x component will give you a sine function. So you need two detectors that can detect both your cosine function and your sine function. And also yeah, in quadrature detection we want to detect both the positive frequencies and the negative frequencies. So that is why your carrier has to be placed at the center. It has to be placed at the middle of the spectrum, and it requires two detectors. Okay, so answer is option D. Okay, so one detector measures one component, right? So you have two components. So when your Z magnetization is flipped in the transverse plane, you get two components. One is in the x axis and another is in the y axis. So if you want to detect both the cosine, your cosine function will give you absorptive frequencies and your sine function will give you dispersive frequency. Okay, dispersive frequency. So if you want to detect both the signals, then you need two detectors. So that is why you require two detectors. So one detector will detect the x component, another detector will detect the y component. So that is why x plus y detection will give you the quadrature detection. So answer is option D.
ಸರ್ ಆಪ್ಷನ್ ಬಿ ಅಂತ ಆನ್ಸರ್ ಇದೆ, ಮತ್ತು ಆಪ್ಷನ್ ಡಿ ಅಂತ ಹೇಳ್ತಿದ್ದಾರೆ.
Sorry, option B. Sorry, option B. Answer is option B, middle of the spectrum, and 2. Okay. So your middle, if your detector is placed at the middle of the spectrum, then only you can capture both the positive frequencies and the negative frequencies. Okay. Now folding of signals in NMR spectrum occurs because of, so just now we learnt about the signal folding, right? So when will folding of signals occur? So what will be the answer? So option A is smaller spectral width than required. Option B is wrong pulse width. Option C is dwell time is smaller than the Nyquist equation. And option D is wrong choice of pulse phase. So we just now discussed that if you select a spectral width, so if this is your spectral width that you're selecting, and your signal, if your spectral width is very small, then it can then what will happen? The particular resonance frequency you want to capture, it may lie beyond this spectral width. Okay, and in such a case, what will happen? There can be folding of this particular signal within this spectral width, and you can get a resonance frequency at a wrong ppm value. Okay, at a wrong position. So if your spectral width is smaller than that is required, then folding of signals occurs. So answer is option A. Okay. So the spectral width determines the frequency range that we are observing. If we choose a spectral width that is too small, some NMR signals may actually lie outside the selected frequency range. So this is your frequency range, but your frequency that you want to capture is lying outside the selected frequency range. So that is why the spectrometer, what will it do? It will incorrectly represent those signals inside the observed spectral window. It will represent this particular signal within the observed spectral window, and there will be an incorrect appearance of signal at another frequency, at a different frequency, which is called folding or aliasing. Okay. So so this point we haven't covered yet. So we will come to this question later. I hope these two things are clear. These 2 points are clear. There was one more question that I wanted to discuss. Okay, so this is not being covered. Okay, in the practical aspects of FTNMR, first of all, we learned that your pulse width has to be calibrated, right? Must be calibrated because your pulse width controls the flip angle. Must be calibrated. Second, your detector axis is important, where you place the detector, whether you are keeping it in the x-axis or the y-axis. That is playing an important role in what type of signal you will get, whether you will get an absorptive signal or a dispersive signal. third thing that we are learned is that your spectral width should be appropriate, so that the folding of signal is not observed, right? These are the few points that we covered. And another is the carrier frequency and the offset. So you might have to increase the frequency of the spectrometer to capture the particular resonance frequency by a few kilohertz. Now another thing is that the signal averaging and repetition rate. So so this is from the lecture slide. So as it was explained in the lecture, that you are applying short RF pulses, right? And then you are so this is the RF pulse that you applied. Then you are removing that RF pulse, and then you are capturing the free induction decay. Then again you are applying that particular RF pulse, then again you are capturing that free induction decay. So in this way, you are capturing multiple free induction decay, FID1, FID2, FID3, and the sum of all these free induction decay will give you that will so your free induction decay will be superposition of all these different free induction decay. So now the duration between two RF pulse should be is the duration between two RF pulse is given by TP. Okay, TP. So this has to be optimized. Your beta. So what is your flip angle beta, and what is the duration between two consecutive RF pulses? That should be optimized, and it is given by this equation, like mx equal to m naught sine beta 1 minus e1 by 1 minus e1 cos beta. So your E1 that is there, it is equal to e to the power minus TP by T1. So maximum amplitude will be obtained for a beta optimum, for a beta equal to beta optimum when your cos beta optimum equal to E1. So so that this is what I was trying to explain. So if you are applying, when you are applying that particular RF pulse, you are if you are applying a particular RF pulse, and then you are capturing the FID and the duration, and then you are waiting for a time t which is denoted by TP. So TP is basically the duration between two consecutive RF pulses. So TP between is the time between successive RF pulses, and this TP should be optimized. That the duration must be optimized so that every time the magnetization that you are capturing will be the same. Yeah. Okay. So the magnetization initially changes from scan to scan. Eventually, it reaches a steady state. At steady state magnetization, before every pulse becomes same, so it should be such that your FID1, FID2, FID3, every so you are scanning, right? You are at every scan. So by multiple scans, what you are actually doing, you are actually improving the signal to noise ratio. You are increasing the signal of the nuclei that you want to capture. So at every scan, you want your FIDs to remain the same. So that is why you have to optimize your flip angle and your and the duration between successive pulses. Okay. So another thing is that if your T1 is very large, so your beta optimum is varies with this TP by T1 following this curve. So if your T1 is large, then you will best signal to noise ratio per unit time is obtained for small flip angles. So if your T1 for certain nuclei, so for nuclei like quaternary carbon or carbonyl carbon, they have very long T1 values. So for nuclei which have very large T1 values, you would always want the this flip angle to have a small value. Okay, you will always want that this beta optimum should be small value. So you will not keep the flip angle to 90 degrees. So if you keep the flip angle to 90 degrees, then what will happen? Then all the entire magnetization will move to the XY axis. Now before the nuclei gets the time to decay, or before the transverse magnetization is completely decay, you apply the next pulse sequence. So the signal will not be captured, entire signal will not be captured. So for nuclei which have very large T1 values, you will always have to keep the beta optimum to small values. You will always have to keep small flip angles. So basically at steady state, your transverse magnetization is given by this equation: mx equal to m naught sine beta, 1 minus e1 by 1 minus e1 cos beta, where e1 is equal to e to the power minus tp by t1. So maximum signal will only be obtained at when your this cos beta optimum value is equal to e1. Okay, and your cos beta optimum is what? E1 is what? So your E1 is e to the power minus TP by T1. Okay, so you can like put this value. So this angle is this beta optimal angle that you obtain from this equation is called the Ernst angle condition. So at this particular angle, you will have the maximum signal. Okay. So you have to optimize the beta value, which is called the value of beta at which you get the maximum signal, is the beta optimal value, and you have to also optimize the TP value. So you have to optimize this beta value and the TP value, so that you can get the maximum signal. And for nuclei which have large T1 values, you have to keep the beta angle small. Beta angle must be kept small. So if you keep the beta angle small, only then this this transverse magnetization can be fully captured before you apply the next RF pulse. Okay. So this we have discussed. Now coming to this question. So for a molecule with large T1, the appropriate flip angle. So this is based on the concept that we discussed just now. So if a molecule has a large T1 value, then what would be the appropriate flip angle to obtain the best signal to noise ratio per unit time by signal averaging? So if you look at the options, now you can just if you understand the concept that if your molecule is having large T1 value, then you have to keep the value very small, beta value very small. Only then you can capture the entire magnetization before the next RF pulse is applied. So if you look at these options now, then there are out of all these options, this 30-degree is having the least angle, right? 30-degree. So the options are so actually correct answer for this question is option A, 30 degrees, 60, 90, and 120-degree. Now you can put all those values, and you can put it in the equation and solve those equation and get the value. But this is not this question is not does not require you to go through those equation. It is just based on the concept that if your T1 value is large, then you have to keep the beta angle very small. So very small means the minimum angle for this is in this option is 30-degree. So that is the answer. Okay. So large T1 value will give a smaller optimum flip angle. So for large T1 value, what happens is that the longitudinal magnetization recovers slowly between successive scans. Right. So the longitudinal magnetization recovery. So when you are applying that RF pulse, there will be growth in the transverse magnetization, and there will be decay in the longitudinal magnetization. Now, when the pulse is removed, your there will be decay in the transverse magnetization, and there will be growth in the longitudinal magnetization. So you have to provide sufficient time to allow the growth of the longitudinal magnetization. So unless that longitudinal magnetization has been completely recovered, you cannot apply the next pulse. So that is why you have to so what will happen? So in that case, if you use large flip angles such as 90-degree, that would deplete MZ substantially before it has recovered. Okay, so therefore a small flip angle is preferred for rapid signal averaging and better signal to noise per unit time. This optimal flip angle is called the Ernst angle. So for large T1, we keep the optimum flip angle very small. So answer is option A. Now, we had also learned about the phase correction. Okay, so just now we learned that when we are applying that RF pulse and we are capturing the signal in the transverse when we are capturing the signal of transverse magnetization, we get two types of signal. One is the signal which follows the cosine function, and another is the signal which follows the sine function. So your cosine function will give you absorptive signal, and your sine function gives you dispersive signal. Will give you dispersive signal. Okay. Now what happens is that your all the absorptive signals that you obtain, they are not 100% absorptive, and all the dispersive signal that you obtain, they are not 100% dispersive. There will be some absorptive components as well. Okay, so FTR, so that is what is explained here. So FT, so for that to obtain the completely absorptive signal and complete dispersive signal, you have to do a phase correction. So FT-NMR can produce two types of signal. One is the absorptive signal. It is also called as the 0 degree phase, and another is you can get a dispersive signal, which is called as the 90-degree phase signal. So now each of these signal, this absorptive signal consists of a real part and imaginary part. Similarly, the dispersive signal will also consist of a real part and an imaginary part. So in case of absorptive signal, the real part is purely absorptive signal, and the imaginary part is purely dispersive signal. But in practice, what happens? In practice, the spectrum may contain a mixture of absorptive and dispersive component. This mixture is called a phase error and must be corrected. So as was explained in the lecture, so this is from the lecture side. You can see that, so that is what is explained here, that when you are doing an FT-NMR, you can obtain two types of signal, right? You can obtain an absorptive signal, which is also known as a 0 degree phase signal, and you can obtain a dispersive signal, also known as the 90-degree phase signal. Now, if you do a Fourier transform, of this cosine function, then the Fourier transform of this cosine function will give you two parts, a real part and an imaginary part. This real part is absorptive and the imaginary part is dispersive. Similarly, if you do a Fourier transform of this sine function means the signal that you were detecting in the x-axis. Your x-axis signal gives you the sine function. So when you do a Fourier transform of this sine function, then again you get two signals. One is the real and another is the imaginary. So your real part is 100% dispersive, and your imaginary part is will be 100% dispersive. Now, what happens is that your so each of the spectrum, so the cosine function. So if you do the cosine function, there will be some absorptive signals, there will be some imaginary signal. You want that the cosine function should have 100% absorptive signal, and your sine function gives you 100% dispersive function. But what happens if there is an error in the but when you are recording the signal, there can be an imaginary part, or there can be some dispersive signal in the cosine function, and there can be some absorptive signal in the dispersive signal. So that is what is there. The spectrum may contain a mixture of absorptive and dispersive components, and this mixture is called a phase error, and that has to be corrected. So that is what is explained here. So in the phase, sometimes we get what? We get a mixture of absorptive and dispersive signals. So your absorptive signal will not look exactly like this. It may look somewhat, it may have this absorptive signal, but you can also get a little bit of dispersive signal. Okay, so that is the phase error. This is the phase error, which means that your absorptive signal will have some dispersive signal in it. So as you can see that it was explained in the lecture, sir, that your absorptive signal is having a mixture of absorptive and dispersive signals, and this is the phase error, and this has to be corrected. Okay, so why does this happen? Is it why do we get a mixture of these two signals when we are applying a particular pulse? Why do we get this signal? So what happens is that if your if the if your yeah, radio frequency pulse is not applied at a particular time, so it has to be applied at time t equal to 0. But if there is a delay in the time, okay, or it can be it can happen that it is that it is not exactly applied at that at the x direction. There can be so you want that z magnetization to come to the y axis. When you are applying the 90-degree x pulse, you want the entire z magnetization to come to the transverse plane, basically. Either in the it will come to the y-axis, or it will come to the x-axis. But what happens that if there is a tilt, or if there is a tilt in the application of the RF pulse, if it is not exactly at that particular position, then what will happen? It will now not exactly, your magnetization will not exactly come at the y-axis. It will be tilted. It will lie somewhere in the xy plane. So you can see here, so it can lie somewhere in the xy plane. And now if you break this, if you resolve this into two components, it will you will have a component in the x-axis, and you will have a component in the y-axis. So that is why your now you will not have purely absorptive signal. You will have a cosine component coming, and you will also have a sine component coming. So your cosine component is what? This is your real part. This is your real part, and this is your imaginary part. So your real part is purely absorptive, and because you are having a sine component, it will also have a dispersive signal. So now when you add these two, this real part and imaginary part, you have this type of signal. So I think so. Is this clear? So you are not applying the pulse at exactly at the x-axis. If there is a tilt from the x-axis, then your component will not exactly lie in the your magnetization will not come to the y-axis. It will be shifted. It can lie in a plane in the xy plane. So that is called as the zero order phase error. Okay. Why is it called as the zero order phase error? Is because at t equal to 0, all the components, so all the nuclear components will have the same phase error. That is why it is called as the zero order phase error. So that is so a correct 90-degree RF pulse along x-axis. So if you apply the RF pulse exactly at the x-axis, then that will rotate the initial magnetization m naught exactly onto the y-axis. Okay, so your magnetization will exactly move from the z-axis to the y-axis. So if this is your y-axis, this is your z-axis, this is your y-axis, and this is your x-axis, your bulk magnetization will exactly move from the z-axis to the y-axis. Okay, this axis. But because your FID is what? It is proportional to, just now we learned, right, that mx is equal to is just proportional to cos omega I t e to the power minus lambda I t. So after Fourier transformation, you get the real part absorptive. But if it is not exactly at the correct, so if the pulse is slightly misaligned, so if it is misaligned, then the magnetization will now not lie exactly along the y-axis, and it will have components. It will lie somewhere in the xy plane, and now it will have components in both the x-axis and the y-axis. So your x-axis will now, if you break it into components, your x-axis will give you sine function, and your y-axis will give you cosine function. So now you are having both the dispersive signal. Sine means you will get dispersive signal, and your cosine will give you absorptive signal. So your absorptive signal will not be purely absorptive. It will be a combination of both the absorptive signal and dispersive signal. So your absorptive signal now will not look like this. It will be a combination of this and this. Okay, so you have to do phase correction to correct this signal from this. So you want the this error, phase error. So this is called zero order phase error. So after correction of this zero order phase error, you can get the signal converted from this signal to this purely absorptive signal. So if the initial phase error is theta, is that it is misaligned. You are applying the RF pulse not at exactly the at 90-degree x direction, but it is misaligned, and it is shifted to a theta angle. So the resulting spectrum will now contain a mixture of both the absorptive and dispersive signal, because the phase error is independent of the frequency. So this phase error is independent of the frequency. At t equal to 0, all the frequency components will have the same error. So it is called a zero order phase error. So zero order phase error will give you same phase shifts for all resonances. The computer mixes the real and imaginary component appropriately to eliminate the unwanted components. So what is your goal? Your goal is that you want that the real part should be purely absorptive and the imaginary part purely dispersive. So this phase correction is now, we do not have to do this. There are these softwares. It is already fitted in the in the system, and these adjustments are done by what it does is it appropriately mixes the real and the imaginary parts to eliminate the phase admixture. So this particular component, if a particular function is added, then by adding that particular function we can remove that the component, that dispersive component that we were getting. So the solution for this is that you have to mix the real and imaginary components appropriately, so that you can get the purely absorptive signal and the purely dispersive signal. Okay. So that is what the computer mixes the real and imaginary components appropriately to eliminate the unwanted component. So that is what was explained in the lecture as well. So you mix the real and imaginary parts appropriately to eliminate the admixture. So this is manually adjusted. Okay, so that your real part is now purely absorptive and your imaginary part is purely dispersive. Okay, now another, so that was zero order phase error. So first order phase error is what? So zero order phase error is when your RF pulse is misaligned. It is your 90-degree X pulse is not exactly at the applied at the X axis. It is somewhat oriented at an angle theta. So that is giving you zero order phase error, because all the nuclei are now having the same frequencies. Okay, they are having the, it is independent of the frequency. Okay, now there can be a delay in data acquisition. So just as soon as you apply the RF pulse, and once the RF pulse is removed, you have to capture you want that the FID should be captured. But what can happen that, so ideally you want that the data collection should begin at t equal to 0. But practically there may be a small delay t naught before the acquisition begins. So this delay can arise from hardware limitations or practical reasons. And so now what happens is, now you are getting another component. So it was earlier, it was cos omega I t, but because there was a delay in acquiring the signal, now what can happen is that there can be a time t naught added to this cosine function. So the acquired signal now becomes cosine omega I t plus t naught. Now during this acquisition delay t naught, different frequency components processed by different amounts. Therefore, each resonance acquires a different phase shift. Okay, because there was a delay in acquiring the signal. Now these transverse components, they will, all the different nuclei that are present, they will start processing at different frequencies. So all the nuclei will have different phase shift, and they will have different frequency components. So this is called as frequency dependent phase shift or first order phase error. Okay. Now last concept about the practical concept was that dynamic range in FT-NMR. So what is the dynamic? So we learned that the different signals that are obtained, they're digitized. They're digitized. The FID signal that you get, that is continuous, but that has to be digitized, and it has to be stored in the binary form in discrete at discrete time points. So FT NMR excites all signals simultaneously. Therefore, FT contains the sum of contributions from all signals. So that is what was there in the lecture as well. So in FT NMR, all the frequencies are excited together, and the signal is digitized. So the data point that you are getting, so these are the different time at which you are recording the signal. So all the data that you are getting, that is analog, in the analog form, and it has to be converted into the digital form, in the binary form, that is 2 to the power 0, 2 to the power 1, 2 to the power 3. So there can be 4-bit digitizer, 8-bit digitizer, 12-bit digitizer. So 12-bit digitizer would mean that 2 to the power 12 signals can be captured. So the FID is converted into digital data using an analog to digital converter. The ADC stores the signal in the binary form. So for a 4-bit ADC, 16 possible levels exist. So the largest. So what happens is that there is one channel is kept reserved for the positive and negative, or 1 bit is used for the negative and positive sign. So always the number of possible levels, or the number of possible bits that are present, is always 2 to the power n minus 1. Okay, so remember this. So one bit is always kept reserved for the positive and negative sign. So that is why, for example, you have a 11-bit digitizer, then that would mean that you have actually 2 to the power 11 minus 1. So 2048 minus 1, that is 2047 bits. Okay. So what is the dynamic range problem? So suppose we record a proton spectrum of a sample in water. Okay, so for example, you are recording a protein sample, NMR spectrum of a protein sample. Now your protein is present in some buffer, and it will also have some water. Water will also be present, right? So now the proton concentration of water is we are considering that, for example, the proton concentration in this water is 110 molars, but the sample concentration is 1 millimolar, 10 to the power minus 3 molar. So the sample is like it is 1.1 into 10 to the power 5 times in lower concentration than the proton concentration of water. So now what will happen, because your signal from the sample is very less compared to the proton signal of the water. Your the water signal is approximately 1.1 into 10 to the power 5 times stronger than the sample signal. So you will not observe the sample signal, you will only observe the signal of the water proton. Okay, so that is the dynamic range problem. So you have to suppress this water signal so that you can recover the signal from the sample. Okay, so but the example ADC can represent only up to approximately 2047 bits. So the small sample signal may be lost or poorly represented. So this is the dynamic range problem. So for example, it is if it is a 11-bit digitizer, then it can capture only 2047 bits of data points. And yeah, it can happen that your sample signal may be lost because of uh, because of this because of the large signal of the water protons. So the solution is to suppress the strong signal. In many cases, the strongest signal is from the solvent, and if the solvent signal is not of interest, so if the solvent signal is not of interest, then what we have to do, we have to basically suppress the solvent signal. So this allows the weaker signals from the actual sample to be observed. So what does that? So just now we discussed, so that's the same thing. Analog to digital converter. What it does is, in FT-NMR, the signal detected from the NMR experiment is an analog signal, which is continuous in time and amplitude. Analog signals means what? They are getting a continuous signal, which is continuous in time and amplitude. This analog signal needs to be converted into a digital signal for further processing and analysis. The resolution of an FID of an ADC. Resolution of an ADC is the number of bits it uses to represent the analog signal. So the analog signal that was there, that has to be digitized. So the number of bits must be sufficient so that all the signals can be captured, right? To so that the entire analog signal can be represented. So the dynamic range of an ADC in FT-NMR refers to the ratio between the largest and the smallest signal intensities that the ADC can actually represent. So it is a crucial factor because NMR signals can vary greatly in intensity, and the ADC must be able to capture both large and weak signals within the same experiment. A large dynamic range is essential in NMR because it allows the detection of low intensity signal. So if you keep the dynamic range large, then the low intensity signal can also be captured. So basically, ADC, the resolution of your ADC is depending on the maximum signal and the lowest signal, largest signal and the weakest signal that it can capture. Okay, so you have to keep the dynamic range large. So the number of bits used by the ADC determines the number of discrete levels it can represent. An ADC with n bits can be represented as 2 to the power n levels. However, for signal representation, considering 1 bit for sign, it effectively represents 2 to the power n minus 1 levels. Okay, so now answer this question. If you have understood the concept of dynamic range, there are few questions. So consider an FT-NMR with two signals of intensity ratio to 2048 is to 1. So what is the minimum ADC bit required to represent both signal? So your maximum signal is 2048 and your minimum signal is 1. So what is the minimum ADC bit required to represent both signal? So answer has to be 11. It has to be 12, right? Because one bit will have to be kept for the considering the sign of the frequency. There has to be, so if you keep 2 to the power 11, then what will happen? So if you so the number of bits required to cover the dynamic range, it is excluding the sign. So 2 to the power 11 would be sufficient to capture 2048, but you have to reserve one bit for the required for the sign conversion. So the minimum ADC bit required will be actually 11 plus 1, that is 12. Okay. So you have to reserve keep one bit extra for the required for the sign conversion. So the answer will be 12 and not 11. Okay. So you have a sample with three signals of intensity 8502 in arbitrary units. If the ADC has a 14-bit resolution, 13 bits for signal representation, and 1 bit is for the sign conversion or for the different sign. So determine whether all the three signals can be accurately recorded. So if the ADC has a 14-bit resolution, then what will happen? So if you do 2 to the power 13, then what is 2 to the power 13? So what is 2 to the power 13? 2 to the power 13 is 8192 hertz. Or 2 to the power is in arbitrary units, it is 8192. So all these three intensity of signals, 8502, they are all lying within this 8192 ADC range, or it is lying within the dynamic range. So if you are having a 14-bit resolution, then your all the signals can be accurately recorded. So answer is yes. So if you have to, so you have been asked that determine whether all the three signals can be accurately recorded. Then yeah, answer is yes. They can, or they all can be accurately recorded because they are all lying within the dynamic range. Okay. So now this answer this question. So in a free induction decay, if the first data point has zero intensity, so if your first data point has zero intensity, then what can happen? So if your first data point has zero intensity, your FID can either look like this,
Hello,
or
sir.
your yeah, sorry,
In the previous questions,
yeah,
next another previous questions.
in this question,
In this question, they are telling FT NMR two signals are in intensity ratio is 2048 is to 1.
yeah.
What is the minimum ADC bit required to represent the both signals ಅಂತ ಹೇಳಿದ್ರಲ್ಲ. ಸೊ
Hmm.
ನೀವು 11 ಕನ್ಸಿಡರ್ ಮಾಡ್ಬಿಟ್ಟು ಪ್ಲಸ್ ಒನ್ ಆ್ಯಡ್ ಮಾಡಿದ್ರೆ ದರ್ ಇಸ್ ಎ 12 ಬಿಟ್ಸ್ ಅಂತ ಹೇಳಿದ್ರಿ. ಅಂದರೆ ಸಿಗ್ನಲ್ ಕನ್ವರ್ಷನ್ ಆಗ್ಬೇಕಾದ್ರೆ ಒಂದು ಆ್ಯಡ್ ಮಾಡ್ಬೇಕು ಅಂತ.
Yeah. So actually, what you are saying is correct. So if you have to just represent both the signals, then 2 to the power 11 is sufficient, right? Because your 2 to the power, if your dynamic range is 2 to the power 11, then that would cover both the highest signal, maximum signal, and the minimum signal. So, but always you have to keep one bit assigned for the sign conversion. So that is why you added 1 to that. 11 plus 1, 12. So you what you are
So from
asking?
the next question,
Yeah.
so here what is the questions for telling that there is 11 bit resolution, the
uh,
13 bits for a signal representation.
yeah.
So we are considering only 13 bits.
For signal representation, okay. Yeah.
Okay, we are adding 14 bits. We are minusing one in this question.
One. Actually, yeah, what you are saying is correct. Actually, this question answer should be 11, isn't it? If we go by this question as well. So for
Yes,
signal representation 11 should be sufficient. Okay. 11 should be
sir. That's I'm
sufficient.
telling.
Yeah, yeah. Yeah, yeah, what you're saying is actually correct. 11 for just representing the signals, then 11 bits should be sufficient. You do
Yes, sir.
not require that extra one bit for the signal.
If in this question we are adding a signal conversion plus one,
Yeah,
and next questions we also add the one signal conversion.
yes, yes, yes.
So, sir, one question,
Hmm.
sir, we able to change the timings of this class from 5 to 7?
Okay, you want it from 5 to 7.
Yes,
So
sir.
all of you want it from 5 to 7. Uh, okay, I can.
Because we are not in the room. We are still in the college.
Okay, okay.
but it's
Oh,
already too late.
okay. So if I shift it from 6 to 8, is it fine? Like,
Six
uh,
to eight. Okay, it's fine.
okay,
5 to 7 hours, it's okay for all.
it would be better. Okay.
Yeah,
Okay, okay. I'll keep it from 5 to 7 in that case. I will.
because it's
Yeah, you will
already 9, but
receive.
it's too late already.
Yeah, it's becoming late. Yeah. Okay, so I will from before the next class you will get a revised. The timing will be revised. Okay.
Okay, okay, sir. Thank you.
So there are two more questions, and then we will end today's session. Basically, what you have been asked in this question is that the first data point has zero intensity. So if your first data point has zero intensity, then your FIT can either look like this or it can also look like this, right? So this, if you do a Fourier transform of this FID, you get a positive absorptive signal, right? You get a positive absorptive signal, like your absorptive signal would look like this. And if you do a Fourier transform of this FID, you get a negative absorptive signal. Your absorptive signal will look like this. Okay, so this is negative absorptive signal. But in both the cases, they are absorptive signals. So if your first data point is zero, then it will always be a absorptive signal. Okay, it will always be a absorptive signal. So there are actually no option of negative absorptive signal. There is only one option which says that positive absorptive signal, negative absorption signal. Actually, answer will be both A and B. Okay, you can either have first data point has zero intensity. If your first data point has zero intensity, then what will happen?
There is maybe answer mixed of both absorption and disruption
Uh,
signals.
hmm. uh, no, actually, the answer is option C. Uh, has zero intensity. Okay. So this zero intensity. Yeah, zero intensity we learned, right? No, no. I made a mistake actually. Sorry. So if it is having zero intensity means what? It is a sine function, isn't it? If it is a zero intensity, your sine component will what? Because your sine function always starts with zero, right? If it is a cosine component, if it is a cosine component, it will start with a particular amplitude. Okay, and we have been discussing throughout the lecture is that your sine component, if you do a FID of a sine component, you get dispersive signal. Sorry for the confusion. Actually, I got confused. Is it clear? Your sine component, if you do a Fourier transform of a sine component, you will always get dispersive signal. Okay, you will get dispersive signal. Okay, it can either look like this, it can either look like this. Because your first, is it clear? Who was asking
Yes,
the
sir.
question?
Okay, but
Yeah,
sign indicates the y-axis, no?
yeah. Sine indicates the y-axis. Yes. So so actually there are no option like positive dispersive signal and negative dispersive signal. So answer is dispersive signal. You can either have positive dispersive signal if it is starting from zero and going to negative, or if it's starting from negative going to positive. So okay. So zero intensity means it is a sine function basically. That is what is the concept of this question. It is a sine function, and if you do a Fourier transform of sine function, you will always get a dispersive line shape. Okay.
Okay, okay.
And if it is starting from some amplitude, means it is a cosine function, right? Because cos zero is never equal to zero. It's cos zero is one, right? And sine zero is zero. So that is why zero intensity. When you are getting a zero intensity after Fourier transform, it means that it is the sine function. Okay. So this question we just now discussed. The in NMR, the loss of small signal of sample due to large signal of solvent is what? So due to just now we discussed the concept of water. So your water proton is having very large signal of 2 to the power of 110 molars compared to your sample. So if your sample has a concentration of 1 millimolar, 1 into 10 to the power minus 3, then this large signal will suppress the small signal of water. So that's why in the later lectures we also learnt about the water suppression peaks, and how we can suppress the water peaks. So that is the dynamic range problem. Okay. So that was all for today. So answer is option B. If the FTNMR signals from solvent and sample are detected together, uh, the solvent will produce a very large signal compared with the sample signal. So the detector or ADC has a limited dynamic range and may not represent a much weaker sample signal properly. Okay. So this was the last
Okay, sir.
question.
Okay.
Yeah. I think.
Okay, sir.
Okay. There is one more question. Just solvent preparation we will discuss in the next class. We will revise those concepts. But zero order phase error in an NMR spectrum is what? So we discussed about two concepts. One was zero order phase error and first order phase error, right? So zero order phase error comes when your RF pulse is not aligned. RF pulse is not aligned properly, or it is not aligned exactly at the x-axis or y-axis. Whatever, anything can be the direction. It can be either you are applying the RF pulse in the x direction, or it can be you are applying in the y direction. Is not aligned exactly. Then what will happen? In that case, all the frequencies, the error, all the sample will have the same error, and it will be independent of the frequency. So that is why it is same. Is same zero order phase error is same throughout the spectrum. Answer is option B. Okay. So zero order phase error is independent of frequency. It is independent of frequency. It occurs when the initial RF pulse is not applied with exactly the correct phase. So if you are not applying the RF pulse at exactly the correct phase, then as a result, what can happen? The magnetization is not rotated exactly onto the desired axis, and we will get a mixture of absorptive and dispersive component. But in zero order phase error, all the frequencies will be the same for all the nuclei. Same, there will be same phase error for all the frequencies. So that is why. So whether we look close to or far from offset, the phase error will remain the same. That is why it is same throughout the spectra. But another was first order phase error. So first order phase error comes when there is a delay in acquiring the FID signal. So if there is a delay in acquiring the FID signal, then all the nuclei will now start precessing at different frequencies, and some will be captured later, some will be captured earlier. So as a result, all the nuclei will have different frequencies. So that is option B. So I hope this we could cover some of the points that were covered in the that we had already seen in the lectures. Uh, so, is there any doubts on what we have discussed?
No doubts. Okay.
Okay, we will take up more concepts in the next lecture. Okay,
Okay. Okay.
thank you
Bye.
so much.